Boom. Hello and welcome back to Calculus 3, section 11.7, motion in space. See, it's not easy. It's not easy what I do. Motion in space. That means we have to have what? We have to have some kind of path, right, that measures the position of the object. And we have velocity, we have speed, we have acceleration. All of which are going to be vector components, all of which are in 3D, all of which are explained through the parametrization using vector-valued functions. So we start by understanding that the position is good old vector r parametricized over t, which we can use f, g, h, x, y, z of t, whatever the hell you want to use. So x of t, y of t, z of t, which gives us the location where the object is. So if I am to just put a random curve of some kind and call that r of t, we are going to have a location which is x, y, z, and then we are also going to have a vector r and this location happens at t equals some value, 1 second, 10 seconds, 3 years, depending on what you are tracing, what you're measuring. So the point in space and the vector have same numbers, right? Point has parentheses, vector has the spiky brackets, right? Points towards the point. The point is at the terminal point of the vector. So we understand the position. So if I say t equals a1, t equal, right? So we follow the progression of the point. Let's say a1, a2, a3, a4, a5, and so on. So this vector r, given functions x of t, y of t, and z of t, we can trace the location of the object in space. And now we just hit this vector with Calc1, the derivative. So the derivative of vector r in respect to time, which we denote by r prime of t, is going to be the velocity vector, but it's just taking independent derivatives, right? Calc1 derivatives. So x prime, y prime, and z prime of t. Again, vector valued function. This time it has all of the derivatives in there. Now that gives us velocity. Remember that vectors have direction and magnitude. Now what we can do is we can find the magnitude of the vector, which is the good old square root of x prime of t squared plus y prime of t squared plus z prime of t squared. And this is what? Thank you. All of the physicists in the classroom, it's speed, right? So speed is the magnitude of velocity without having any of the direction, right? It's just a scalar quantity. So, you know, when you see a speed limit, it's sufficient to write speed limit because they're hoping you're going to go with the flow of the traffic, right? 65 miles per hour, hopefully with the flow, right? If they said velocity acceleration, they would have to say 65 miles per hour forward, right? Because then you are giving the direction as well, right? So that's something important. So speed just tells you the magnitude of the vector, magnitude of the velocity. So that's your miles per hour. And then we can take one more derivative, and that gives us clearly the acceleration. So we are looking at the second derivative in respect to time, double prime, right? Which is x double prime, y double prime, and z double prime. That's acceleration of the object. There is one more. What is the another step? Jerk. Yes. So the next derivative, which is not discussed in the textbook, is jerk, and that's where the journey ends. So you have the position, and then and then you have velocity, which is change of position. You have acceleration, which is change of the velocity. You have the velocity is change of position, acceleration, that is change of velocity, and jerk is change of acceleration. So in your car, for those of you who didn't take my Calc 1, I explained this in Calc 1 class. So when you're in your car, you have two pedals. One is gas and one is brake. Both of those are acceleration pedals. Well, one is deceleration, but it's just negative acceleration. So when you push the gas pedal, you are changing velocity, which means the gas pedal controls acceleration. Now, you can press it lightly or you can slam on it. The same thing with brakes. You can apply brakes lightly or you can slam on the brakes. The difference, whether you are slamming your face in the steering wheel or not, that's jerk. That's that part. So the rapid change in acceleration is felt right by us, and we call it jerk. So that's the next derivative. It's not discussed here, but you might run into it in your physics textbook. Now, talking about the graph again, I'm going to again put some kind of the path over there. At this point here, which is position in space, which we measure looking at our vector r of t, at that point we are going to have a tangent r prime, which is the velocity vector, and then we are going to have, let's use purple, r double prime, which is the acceleration. So at any point you will be experiencing all three: acceleration. If acceleration is 0, then you are experiencing constant motion, right? Constant velocity. If acceleration is not 0, then you're either speeding up or slowing down. That's all of the parts. So first, to see how these components work, we take a look at the two-dimensional case. You can tell that I spent the whole break practicing drawing circles. Look how perfect that is. So this is a path. It's a circular path. We are going to describe this. So let's say this is 3. It is 3 units. So the r, which is the path on which put the particle somewhere, is going to travel, is going to be 3 cosine t, comma 3 sine t. So this is a two-dimensional path. Therefore, we only need 2 dimensions in our parametrization. And we can quickly find the velocity vector, which is r prime, as negative 3 sine t and 3 cosine t. And we can find acceleration, the double prime, which is negative 3 cosine t and negative 3 sine t. So now, if you are to observe, let's say, a position over here, t equal to 0, so for t equal to 0, your r of 0 is 3, 0. So the position vector points towards the location. The terminal point of the vector is the location of the object. Since it's t times, so t equals 0, that's the initial position. Now, at that point, we have a vector r prime, which is the velocity vector, which is going to be 0 and 3. Now, 0, 3 vector from the position where the object is this one. So this is your r prime of t. So the red one points to show where the object is, and then you create a new set of coordinate axes at the location where the object is. You regard that as 0, 0, and you draw a velocity vector and acceleration vector from that point. That leaves us with a purple r double prime, which is negative 3, 0. Negative 3, 0, again, from the object is going to be this way. So now we can follow this pattern around. If you carefully observe, you see that this blue vector is forcing the counterclockwise motion. Do we see that? And if you are to compute one more set of this data, let's say at t equals pi over 2, because we can, r at pi over 2 will be 0 and 3, which is vertical up, giving us the position at 90 degrees, right at 12 o'clock if you want. And then the velocity r, we plug everything into the velocity equation, so we get negative 3, 0. We create new coordinate system 0, 0 at the location here, right? That's where you get the 0, 0 coordinate now. And we draw negative 3, x and 0, so it looks like this. And that's your r prime of t. And then purple, the acceleration at pi over 2 is going to be 0, negative 3. So from here we can clearly see that all of the, and it doesn't matter where you draw, you can draw here, right? It's going to look like that. It's going to be perpendicular. So we see that the blue is trying to rotate the whole motion to go counterclockwise. Observe that acceleration is pulling inwards, and the object is keeping orbit. You can think of that, and the role of this purple acceleration is the gravity that keeps the planets in orbit around the sun. Yeah, it's not a circle, but it's pretty damn close to a circle. Okay, so you see that somehow the purple vector is taking the object and it's accelerating the object towards the center, right? And you can see that I don't have anything heavy for the other end, but this part, if it's this part is the object is going to stay in the orbit, right? Now, why is it not departing? Because there is what in the string? Tension, pulling it inwards, right? So it stays in the orbit constantly. So whether it's a string or gravity, there is a force that pulls inward as the velocity is pushing outward tangential, right? So if there was no acceleration to pull it inward, right, the object passes off. So now you hopefully understand the motion, and we can just make this more interesting with adding extra components. We evolved on this planet in a way that we don't feel the spin and the velocity of the planet, and then our rotation around the sun and the rotation within the galaxy and so on. Because think about it. The planet is spinning. It's going around the sun. The sun is, the whole solar system is moving. So there's a lot of motion on top of motion on top of motion. And then the galaxy, right? There's a lot of spinning and a lot of motion happening at the same time. We don't feel any of that. We don't feel any of it. So we definitely don't want to stop the Earth from spinning, because everything else would continue spinning. And that will be it. What is the surface rotational? It's like 160,000, or does anyone know? 160,000 miles per hour? I'm not sure. But anyway, the most important part is to understand that, you know, when we are driving 60 miles or 80 miles per hour, it's pathetic. Even the airplanes with like 600 miles per hour, it's pathetic. Compared to speeds that are out there for the planet and rotation. If you are to drive on the orbit, like build a highway in the orbit of the Earth or around the sun, it will take you 1,111 years to go once around the sun at 60 miles per hour. So if you are able to drive 60 miles per hour 100% of the time, it will take you 1,111 years to go around once. That means that the Earth will catch up and crush you 1,111 times by the time you go on once on that path. That's how pathetic 60 miles per hour is. And then all you need to do is to understand that 600 miles per hour, which is what our airplanes are doing, is still pathetic, because that's still 111 times less than what the planet is doing around the sun, on average, right? Because it's elliptical orbit, so it speeds up and slows down. So you can look up at that stuff. But all of those calculations will be based here. The whole trajectory, if you look at this graph here, right? It's a two-dimensional graph. If I want to make this the elliptical orbit, I'm just going to drop these 3 and put 2 there, and there you go. It's ellipse already. And you can immediately study the velocity and acceleration and everything. So if you are able to model your path, so Earth path around the sun is elliptical, and all you need to do is to adjust the 3 and 2 using the proper measurements, and you will have the parametric side. That will be actually a cool thing for the project, now that I think about it. I had something else in mind. I'll think about it. you might learn something. I know. Terrible. Is there anything else I need to talk about? I think I need to talk about so we've seen that the for the circle, the position vector, velocity vector, and acceleration vector are all perpendicular to each other, which means that their dot products are 0. I need two pairs, except if you multiply the acceleration and position. Theorem 11.8 says motion with a constant r. So motion of the circle, velocity, and position vector, the dot product is 0. We just talked about it. So on circular path, output here also holds for the surface of the sphere. The dot product, so r dot v, is equal to 0, the dot product, because they're perpendicular. Now, down the line, if you continue pursuing mathematics, this will lead into more cool stuff to study. Now, how can you prove that objects move on the circular path or the circular path or the sphere? Well, you have the you do the dot product, and if the dot product is 0, then that's it. So the next part is the good old motion in so Newtonian gravity. We look at the 2D case, and then we extrapolate everything into 3D eventually. So 2D motion in gravitational field. So it's 2D motion, right? We have a 2D coordinate system, and then we have some kind of trajectory, right? The path on which the object is moving. It's oriented, it's continuous, smooth, right? No sharp corners and cusps, stuff like that. Discontinuities. And then at the point when you launch an object, there is going to be initial velocity vector v, which is your r prime of t. So the gravity is pushing downwards with negative mg. That's the force of gravity. So the object wants to go up, and the weight, due to gravity, right, the weight is pulling down. And the only thing that it's countering this is the force due to acceleration of the object. Look, if I don't put any acceleration into the object and I let go, what's going to happen? It's going to fall, right? But if I give it some acceleration, initial velocity, it's going to go up until it slows down enough and stops, and when it stops, it's going to fall back down. Now, that's potential kinetic energy at play there. If you remember anything, kinetic energy 1/2 mv squared, right? The mass of the object and then the velocity squared. Remember that the gravity will be slowing it down. So as the gravity is slowing down, the velocity falls. As the velocity falls, eventually will fall to 0. Then the mass times 0, right? Velocity 0, object stopped. The kinetic energy is 0. All of the energy becomes potential energy, which is mgh. mgh is mass times gravity times the height at which the object is. So the height now is the leading factor there. It's a maximum height, so the highest energy. And then as the object starts falling down, what's happening is the velocity, which used to be 0 at the top, is now becoming again positive number. It gets squared, right? And you are losing height, so potential energy is dropping and the kinetic energy is picking up. So it's the game of those two for you to understand how why the object stops and why it moves and so on. But now we have the force of gravity, which is the acceleration downward, and the only thing that counters that one is how hard or how strongly you throw the object up. So we can say, use the same notation, that first let's write that F equals ma. So this is the force equals mass times acceleration. Now this force is actually the weight of the object, so mg, that's a negative mg, equals to ma, from where you see that acceleration is negative g. So we know that gravity is acceleration. Gravity is acceleration. That's why I say acceleration of gravity. Good. So now, looking at the vertical component here, this vector I can describe as 0, negative mg. So acceleration vector is given as 0, negative g. That's the acceleration vector, yes.
Which vector is described as 0, negative mg? The black one? Or the...
This one.
Gravity?
Gravity, yes.
Okay.
Initial velocity. Initial meaning t equals 0 at the beginning of time, is going to be given as v of 0 is equal to, not sure why they're using u0 v0, but I'll follow the same notation as the textbook. Right, so those are the components, and those are numbers, right? Those are numbers. And then we have the initial position, which is also t equals to 0, and in our case that's r. these are vectors of 0, which gives us x0 and y0. So we use these to set up our equations. So all we have is the fact that acceleration vector is 0, negative g. Now, we know that acceleration is change of velocity over change in time. Now we know that. So from here, I can write dv dt is equal to 0, negative g, and then good old differential equation, separation of variables. We have this, and we hit both sides with integral sign. We get velocity in terms of time. That's a vector, right? Velocity is a vector. On the other side, when we integrate, what do we get? We get 0, comma, negative gt plus some constant, and that constant is going to be a vector because we need one for x component, one for y component. So velocity now becomes, remember that it's going to be plus c0, but we have the initial condition here that says, right, says this, sorry, for velocity is one above. It says this, that's the initial velocity up there. So we will have u0 minus gt plus v0. So this is the velocity equation. Starting with this acceleration. Actually, no, the acceleration is on top, right there. So now I know that velocity is change in position over time. In order for you to go from point A to point B, you have to have some velocity. You have to drive 30 miles per hour or 50 miles per hour to get from point A to point B. So change in position over time, which tells us that the r dt, which is the velocity, has this vector u0 negative gt plus v0. And now we do the separation of variables. So dr is equal to u0 negative gt plus v0 dt, and we hit that with the integral on both sides. So now I have the position vector in respect to t equal to u0t plus x0. I'm just going to skip the step of plus c. I'm going to plot this immediately. And then negative 1/2 gt squared. You all know this formula. You memorize this stuff in physics. I don't know if it's derived or not, but there it is. And I'm boxing this one red. You have two components. First component, right? And the second component right here. So what is the first component? What's the first component? Position in x direction, and the second one is position in y direction. Now, do you also see the parabolic motion on the second part? Do we all see the negative x squared, negative t squared? Do we all see that? Yep. So guys, no matter what you throw and how hard you throw it, it is going to have a parabolic motion coming down. So, experiment, there you go. Done, right? So, the y component is in this. So now what you can do, add another component for the 3D motion. You just keep integrating or differentiating term by term. This is application of the last section, which said calculus of vector valued functions. I don't care what you have in terms of, or what I have in terms of the vector valued function. We do this with helix, we do this with anything. If nothing, our planet moves in a helix fashion. Because if you think about it, if this is trajectory on which the sun is moving down the line on the galaxy, and the Earth is going around the sun, then the Earth must be going like this. It's moving forward because the whole solar system is moving forward, and the Earth is constantly going around the sun. But when you combine the two motions, you get the helix motion, right? So you can explore these things and you can find these equations, right? It's not going to be a helix with a circular, it's going to be a helix, elliptical helix, right? But again, you can figure out all of that. And clearly the speed of the sun forward is giving you the z component, right? And the ellipse around the sun is going to give you the motion that has x and y, say. Probably you can find this animation on YouTube somewhere. Has to be. If you're having issues and problems visualizing what I'm talking about. Actually, let me see if it's easy to find. Maybe I can include it in the stream as well. Oh, perfect. It was the first hit. Let's see how this works. There's what? Really? Well, something is unplugged. All right, let me see if I can do it better here. I found the perfect video. Oh, actually, hold on. They have the title of this. There it is. You can already see from the... Oh, actually, you can't see anything. They're not telling me.
Of stars, our entire solar
Still no sound?
is drifting 70,000.
It doesn't matter, but here you go. So you see that the sun
Star Vega in the constellation
goes straight.
Our solar system is part of a giant galaxy called the Milky Way, on a plane tilted about 60 degrees, approximately like the windshield of a car, looking at Earth's North Pole. Our entire solar system races clockwise around the galactic center at about 790,000 kilometers per hour. Our whole galaxy.
Okay, hold on. Listen.
But difficult to notice at big scales, and also don't look like much in the short term. Short, like the length of a human life. Looking from above the North Pole, the equator spins counterclockwise at about 16, 17 kilometers per hour. Relative to the Sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path of 23.4 degrees spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way, on a plane tilted about 60 degrees, approximately like the windshield of a car, looking from above Earth's North Pole. Our entire solar system races clockwise around the galactic center at about 790,000 kilometers per hour. Our whole galaxy is also moving through the universe. We know this because when the universe was very young,
All right.
it was so hot, electrons and protons jumped around, and photons...
You can watch that eventually. But you got the idea. All of that motion is understood through exactly what we did here. You don't need anything else. These are the functions that derive all of that motion. So you will need an elliptical orbit, and then you make that into an elliptical helix, and then with incorporating the correct values for speeds and distances, you get the exact equation that describes how the planet moves. So the equation that you see here is equation for the position, and the equation above is equation for velocity. Now you know these equations as individual equations that you learned in physics. Now we just put them in a vector. We did not learn any new equations. You should be recognizing all of these equations from before. And we will put this into the equation. So now they are talking about the flight of a baseball, but technically anything you throw, it's going to have, all you do is you just plug them into these equations. These are actually already solved. What we did are differential equations, right? Because we did separation of variables. You should know that from Calc 2, separation of variables. We did separation of variables to come up with all of the equations. So we haven't learned anything else. And what happened with half of the equations over here? There's a dt missing over here. And there is the u0 missing over there. All right. So now that's a two-dimensional motion, and for the three-dimensional motion we are going to have again just more interesting, right, because you have one more component, but the calculations still remain the same. So if you are starting from the fact that now the force is going to be 0, 0, and then some negative mg for the object, you see, if I define the wall along which the whiteboard is as the x coordinate, and I throw marker parallel to the wall, we apply two-dimensional equations. Even though we're in 3D space, that axis along the other wall where the door is really doesn't contribute anything, because if I throw it perpendicular, parallel to the x-axis, all of the two-dimensional equations apply. But if I throw it sideways, right, then we have additional component, because now the object is not traveling only in x direction, it's traveling in x and y direction at the same time. Now, in which way they split depends on the angle at which you threw the object. So if I throw at 45 degrees, then these two components will have the same values, right? And the vertical component, in this case now it's z. Z is the one that brings in the gravity to push the marker down. So the two-dimensional equation are still at the same, we still use the same part from position, right, for the z component, but the x component now is going to be broken down using trig of how much you go in one along the x and how much you go along the y. Now, drawing this is always the interesting challenge. So if I have x, if I have y, and if I have a z, and I throw an object, actually, let's throw object along this path there, there's going to be an angle theta here. So the object went this way, but what's important is to understand that there was this initial vector here, the velocity vector v0. Is that how we called it? Yep. Initial vector v0. Now you can decompose, because that initial vector 0 will have the projection, right? Projection on this one. And what you can see is that it has its component. So this is v0x. And then there is also a component v0y. So all of those of you who enjoy statics and dynamics, and you take physics, obviously, you guys will have lots and lots of fun with this. Equations are the same, except they just break. I'm not even sure that they give the equations anywhere. Nope, because you just break the motion down. The y component is the same. Z in this case. So you are going to involve sine and cosine, in this case of whatever theta is, as your components to determine the motion. I think you also do this when you do the kinetic, right, with the billiard balls, when you do the collisions. So I understand that all of this is physics, right? But math is in the base of it, right? So I mean, I won't bother you too much with the 3D cases, but you know, you should look into it. Especially if you're going to take statics, dynamics, and dynamics primarily, right? I'll never forget the challenge question we had when we were a student. Professor gave us a week. No one even came close to the answer. Technically, all of the concepts you ever learn in any of the motion was in that problem. And the idea is you take keys and you throw keys, and when the keys were at the top, the O-ring in the middle snaps and everything fans out. Find the largest radius that must contain all of it. Yep. Now, what do you have? When you throw keys, well, they're spinning. That's the first thing. They're in a parabolic motion. When the O-ring snaps, everything fans out in a parabolic motion, which is now conical. That's 3D. So find the largest radius on the ground that must contain all of the parts. Do what? No, I don't think we.
What about math? How many keys? Ooh.
I don't remember details. It's been a lot of years since. Many, many moons. But just take a keychain with 3 keys and see how beautiful equations work out. Or not. So that's it for this lecture. We should reconvene for one more. Hit the break. Bye, stream.